Hello everyone, this is Anna Bartkiewicz at Nicolaus Copernicus University in Toruń, Poland. I'm very happy to welcome you on behalf of the organizing committee to the second series of seminars sponsored by the European VLBI network and focusing on high-resolution radio astronomy. Let me mention a few logistics. You will be muted throughout the presentation, but you are invited to type in any questions you may have for our speaker through the Q&A Zoom facility or in the chat at the YouTube channel. Questions will be answered only after the presentation. Please try to write your questions clearly and keep them short. We will aim to get as many of your questions as we can, and we apologize in advance if your question is not among those we have time to answer. Before Marcello Giroletti from INAF, Institute for Radio Astronomy in Bologna, will introduce today's speaker, Mar Mezcua, we start with two announcements by Denis Gabuzda from University College Cork, Ireland, and Benito Marcote from JIVE ERIC, the Netherlands.
Benito, do you want to go first or shall I?
You can, please.
Okay, let me just share my screen. Okay, I hope you can see this on this poster I've created. I'd like to encourage you to come to Cork for the 15th EVN Symposium. We've got a great selection of abstracts for talks and posters that we've received now, and the Scientific Organizing Committee is looking them over. And so we have a really good scientific program and a great social program as well. Cork is really lovely. It's a great food city, both for pubs and restaurants and the English market. And there are beautiful places around here, even beaches and beautiful seaside places. And you've got a whole afternoon off. So we really hope to see you in Cork this July. And I'll turn over to Benito.
Yeah, and the last quick announcement is that next Wednesday, you may have seen it, we will have the first EVN users training event. So within one day, 2 different sessions, we aim to basically give you a full preparation for being able to prepare proposals for the EVN and what you can do with the EVN for reach your science goals. And also, if it's the first time that you're observing with the EVN, we are doing a quick scheduled preparation training. So you can get all the information, even if it's the first time that you want or you are using the EVN, this will be a good training. So the registration is open, free, and the event will be next Wednesday from 10 to 12 European time and also 2 to 3. So you can all get all the information in the website.
Okay, now it's time to move on with the talk itself. And so let me give a brief introduction of Mar Mezcua. She's a staff scientist now at the Institute of Space Sciences in Barcelona, Spain. Mar earned her PhD at the Max Planck Institute for Radio Astronomy in Bonn in 2011. After the PhD, she moved to the Canary Islands for a first postdoc, and then on to the Harvard-Smithsonian Center for Astrophysics in Boston. Later, she did another term of postdoc at the University of Montreal in Canada, and since 2017, she is returned back to Spain. Mar is an expert in the study of intermediate mass black holes, and this will be the topic of her talk today. So Mar, please, the floor is yours.
Thank you very much for the invitation to give this talk and for the introduction. Yeah, so I'll be talking about intermediate mass black holes, mainly using radio astronomy, but also I'll talk about supermassive black holes first and about other wavelengths that we use to detect this type of black holes. So I'll start with an introduction to the different mass ranges we have of compact objects. On the low mass end, we have stellar mass black holes with a black hole mass below 100 solar masses. And then the most massive black holes are supermassive black holes with more than 10 to the 6 solar masses. We know there's a gap where no black hole should be formed around 140 to 260 solar masses. And then in between this gap and supermassive black holes is where we should have intermediate mass black holes with a black hole mass higher than stellar mass ones, but lower than the 10 to the 6 solar masses of supermassive black holes. these intermediate mass black holes we think are very important because they could be the seeds from which supermassive black holes form. Now, why is this important? Well, because we have found quasars, supermassive black holes of more than 10 to the 9 solar masses when the universe was very young, less than 1 gigayear. And we can see here a summary from Valiante et al. 2017, in which we have a population of high redshift supermassive black holes of more than 10 to the 9 solar masses at redshift more than 6. The redshift record holder is actually here at 7.6. And then the largest black hole mass is of nearly 10 to the 10. Now, what happens is that these very massive supermassive black holes do not have time to grow in less than 1 gigayear from stellar mass black holes. That's why we have to invoke seed intermediate mass black holes of in between 100 and 10 to the 5 solar masses, which growing via accretion and mergers can become supermassive black holes by redshift 6 to 7. Now, the question that arises is then how do these seed intermediate mass black holes form? And in this sketch, I'm showing different possibilities. Here we have redshift on the y-axis and black hole mass on the x-axis. These are the population of quasars at redshift 6 to 7 with black hole masses of more than 10 to the 9. And these are the seed intermediate mass black holes that can form in the early universe, a high redshift. You see redshifts above 10. These seed intermediate mass black holes can form either from the death of the first generation of population 3 stars, of very massive young stars. This should yield seed black holes of around 100 to 10 to the 3 solar masses. We can have also mergers in nuclear clusters. This would yield a population of seed black holes of in between 10 to the 3 to 10 to the 4 solar masses. And we can also have direct collapse of pregalactic gas disk, which should yield intermediate mass black holes, seed black holes of around 10 to the 5 solar masses. These are the main scenarios proposed so far, although there are some others. And these seed black holes formed here at redshift more than 10 have time to grow via accretion and mergers and become supermassive black holes by redshift 6. However, maybe not all these seed black holes did grow and become supermassive. Those that did not grow should be found in the local universe as leftover intermediate mass black holes with a black hole mass that depends on how they formed in the early universe. If they form from population 3 stars, we should find here intermediate mass black holes of around 10 to the 2, 10 to the 3 solar masses. From direct collapse, we should find 10 to the 5 intermediate mass black holes in the local universe. So as you can imagine, there have been multiple searches for these intermediate mass black holes in the local universe, both in the Milky Way and also extragalactic. And I'll start first by globular clusters in the Milky Way. Why globular clusters? Because as I said, one of the possible formation of scenarios for intermediate mass black holes is via collisions of stars in dense stellar clusters. So there have been many dynamical black hole models applied to kinematic measurements, such as this one here. This is a very famous case, omega Sen, finding that the data can be reproduced by an intermediate mass black hole of 4 times 10 to the 4 solar masses. Another possibility is to have also pulsars with high precision timing solutions, and again, applying an intermediate mass black hole model, such as this one here, applied to observations with the Parkes radio telescope, found that the data can be better reproduced with an intermediate mass black hole. Although note that this model and these results were ruled out a bit later. So in this table, you can find a table of some of the best candidates for being intermediate mass black holes. And I'm saying candidates because although these are dynamical black hole mass measurements, we do not find signatures of accretion in the X-rays or radio from these candidate intermediate mass black holes. The only globular cluster with possible signatures of accretion is this one here, which has Chandra and VLA emission, although the results again were ruled out a bit later. So as you see, the topic is still controversial, whether there are intermediate mass black holes in globular clusters. This is because globular clusters have little gas, little dust, and therefore any signatures of accretion are very low. However, we hope that with the next generation of radio observatories, such as the VLA, next generation VLA, and the SKA, we should be able to detect at least radio emission from intermediate mass black holes in globular clusters. And then apart from globular clusters, we can also have wandering black holes in the Milky Way. These wandering black holes can come from 2 processes. Either they come from globular clusters where black hole encounters have ejected the intermediate mass black hole, or they can come from satellite galaxies that have fallen into the Milky Way that host an intermediate mass black hole, and that as a result of the merger, the black hole has been deposited in the halo of the Milky Way. And these are simulations predicting the numbers of seed black holes coming from population 3 stars and coming from direct collapse expected in the Milky Way stellar halo. In red, I'm showing intermediate mass black holes which are naked, and the ones in blue are the ones that have a bound cluster of stars around. So a population of intermediate mass black holes is expected in the halo of the Milky Way if the seed black holes were common in the first galaxies, in the first dwarf galaxies that merged to form today's massive galaxies, and if these dwarf galaxies merge with a massive galaxy in the form of a minor merger, leaving the wandering black hole in the halo of the most massive galaxy. Such wandering black holes have been predicted to be detected possibly in the radio if signatures of accretion are triggered, for instance, by an encounter with a molecular cloud. And very recent work predict that a detection fraction of around 57% should be found with the next generation VLA, and it should also be detectable with the SKA, as we can see in this image here, simulated at 5 gigahertz. This is in the radio, sorry. In the optical, recent observations and simulations also expect a population of wandering intermediate mass black holes in the halo of the Milky Way with a bound cluster of stars of more than 500 stars, and that should be detectable with the Gaia and Decals survey. And these are the simulations of Green et al. We see here a model image, and here the corresponding stars that should be detectable within more or less 15 arc-second radius. And this is the color magnitude diagram expected using Gaia, which are the red points, and the Decals detection, these gray points. This is what we should detect according to the models. However, in practice, what Green et al. Find is that there are no significant detections. Although this seems to be a cluster of stars, maybe around an intermediate mass black hole, in the end, when you plot the color magnitude diagram, we see that most of the stars are background or foreground. Very few belong to the CMD, the color magnitude diagram. Another work being carried out by my PhD student, Julen Unzaga, is using, instead of Gaia and Decals, pan-stars data. And we are finding overdensities in a similar fashion as previous works. You see here the pan-stars image, the field. Here we have all the stars, and this is the color magnitude diagram. Before correcting for foreground or background stars, and after correcting for foreground background stars. As you see, we seem to have a structure here. And this structure seems to be very similar to that of known globular clusters, where we see there's a red clamp here, an horizontal branch, there's a turn-off here. And in one of our sources, which is a known open cluster, one of the sources we find in the work, we see this kind of red clamp and turnover. In this other candidate, which is an unknown source, we might be seeing a similar thing, but it's not so clear. So this could be a case of an open cluster, but it's not so clear it has an intermediate mass black hole in it. And another place where we can look for intermediate black holes in the Milky Way is in the central molecular zone, which is a zone of dense and warm molecular gas. As we can see here, this is the position of the supermassive black hole in the Milky Way. And these are the inner 200 parsecs seen in CO. And using the Novayama Ray Observatory, what Oka et al. Found is a high velocity compact cloud that we see in here, less than 3 parsecs, with extremely broad velocities, more than 80 kilometers per second, and not detected at any other wavelengths. What these authors did is to apply a gravitational kick model with an intermediate mass black hole, finding that the data could be reproduced by a 10 to the 5 black hole, so an intermediate mass black hole. Therefore, this could be a new pathway to detect intermediate mass black holes in the inner regions of the Milky Way. And this could be performed, for instance, via single dish observations NCO, like with the APEX telescope. These were intermediate mass black holes in the Milky Way, but then we can also look for extragalactic intermediate mass black holes. And I'll start by talking on ultraluminous X-ray sources. ULXs, ultraluminous X-ray sources, are extragalactic and of nuclear X-ray sources with an X-ray luminosity above the Eddington limit for a stellar mass black hole. So we are talking about more than 10 to the 39 ergs per second in X-ray luminosity for a 10 solar mass black hole. Now we know that most of these ULXs can be super Eddington accreting compact objects, stellar mass black holes or neutron stars. However, those extreme ULXs or hyperluminous X-ray sources with more than 10 to the 41, 42 ergs per second are the best candidates to being intermediate mass black holes accreting at sub-Eddington rates and with black hole masses of between 100 to 10 to the 5 solar masses. This is the very first case of an intermediate mass black hole candidate in a ULX. It is HLX1, a very famous source because it has very bright radio emission at the position of the HLX. It's located in a globular cluster, and this radio emission and X-ray emission are transient. Okay, they behave similarly to X-ray binaries. Applying the fundamental plane of black hole accretion, which is a correlation between radio, X-ray luminosity, and black hole mass, it was found that the HLX, this ULX, is consistent with an intermediate mass black hole of around 10 to the 4 to 10 to the 5 solar masses. And because of its location in the outskirts of this lenticular galaxy, it is suggested to be the nucleus of a dwarf galaxy that was stripped in the course of a minor merger with the main galaxy. Another nice example is this one here. This is a spiral galaxy, and the ULX is located in a peculiar spiral arm here, which seems to be compressed. There's no clear optical counterpart, but there's a very bright radio counterpart that we see here in white contours. This is the VLA. We see two peaks of emission of more than 600 parsec size, suggesting that this could be either the jet of an intermediate mass black hole or a giant radio nebula. Using the EVN, we found parsec scale radio emission at the position of the Chandra counterpart, and applying the fundamental plane, we found also for this source a black hole mass that is consistent with an intermediate mass black hole, suggesting that this could be again an of nuclear intermediate mass black hole that was the nucleus of a dwarf galaxy that merged with the main galaxy. And this is another very interesting case because this is a Cipher-2 galaxy. So we know there's an AGN at the center of the galaxy. The galaxy has possibly undergone a gas-rich merger, and the ULX is located here. We see it in X-rays, but also very bright in the radio. In pink, we see here the radio contours. It's not very bright in the X-ray, actually. It has only 10 to 40 ergs per second. However, it has a bright counterpart. We can derive the stellar mass, which is consistent with a dwarf galaxy. And the radio emission, we can resolve it into two components that you can see here, east and west. Applying the fundamental plane, we find again a black hole mass consistent with an intermediate mass black hole. So we conclude that this could be the first multi-component radio jet of an intermediate mass black hole. And because the galaxy has undergone a gas-rich merger, it could be that the ULX activity, that the AGN activity has been triggered by the minor merger. These are a few individual cases, but if you want to have statistical results, we need to go for larger samples. So what we did in 2019 is to cross-match the Chandra source catalog with the SDSS. We did that applying an offset from the galaxy of 5 times the X-ray uncertainty. So to be sure that we are excluding nuclear sources, we are looking for of nuclear sources, and applying an X-ray luminosity cut of 10 to the 41 ergs per second, so that we include very luminous ULXs, so hyperluminous X-ray sources. You can see here some examples. These are the optical images. This is the position of the galaxy. And here in cyan, we have the position of this ULX that you see here in X-rays on this right panel. What we found as a result are more than 100 HLXs. So this is the largest sample of nuclear intermediate mass black hole candidates because they have more than 10 to the 41 ergs per second. Also, many of them have optical counterparts. They are all potentially galaxy mergers. And to confirm that, we applied for HST and GTC Grant-Tecan observations to detect features connecting the primary galaxy with the secondary galaxy hosting the HLX, and also to derive the merger mass ratio, the intermediate mass black hole, the volumetric luminosity. So to test whether there could be any merger-driven black hole growth, and whether the growth of the primordial seed black hole is thus significant. And I'll talk a bit more about this later on. And finally, the last place where to look for intermediate mass black holes extragalactic are dwarf galaxies. Why dwarf galaxies? As I said before, we have here the seed black holes forming in the early universe, and that those that did not become supermassive can be found in the local universe as leftover intermediate mass black hole. Okay, now simulations predict that if the seed black holes formed via direct collapse, which is a very uncommon mechanism that requires certain conditions not easily met, then we expect a low black hole occupation fraction in today's dwarf galaxies, those with a stellar velocity dispersion below 100 kilometers per second. Okay, so in dwarf galaxies, the number of black holes that should be found, intermediate mass black holes, is low if they formed from direct collapse in the early universe. While if they formed via POP3 from POP3 stars, which are thought to have been very abundant, then we expect a high black hole occupation fraction in today's dwarf galaxies. And the formation scenario in the early universe can also leave an imprint on the black hole galaxy correlations, such as the black hole mass versus stellar velocity dispersion, the M-sigma correlation. If seed black holes form via direct collapse, we expect a flattening here in the low mass end of the M-sigma correlation, while if they form from population 3 stars, we expect here a population of undermassive black holes with respect to the M-sigma of more massive galaxies. So as you can see, depending on how seed black holes formed, we can see different imprints in today's dwarf galaxies. But apart from that, dwarf galaxies are thought to be regulated by supernova feedback. This means that stellar outflows evacuate the gas from the nucleus and prevent the growth of the black hole. Also, dwarf galaxies have low mass, and here we consider a stellar mass threshold below 9.5 in logarithmic scale. They have low metallicity, and they have presumably not significantly grown via mergers and accretion since their formation. So dwarf galaxies are the ones that best resemble the first galaxies formed in the early universe, and are thus the best candidates to host the seeds, the relics of the seed intermediate mass black holes formed in the early universe. Because of this, there have been many searches for intermediate mass black holes in dwarf galaxies. Dynamical black hole measurements, there aren't many, only a few, as you can see here in green, out to 4 megaparsecs. Maybe the most famous one might be NGC 4395 that you see here. This is a dwarf galaxy that has an intermediate black hole at the center, based on the detection of broad emission lines, also X-ray emission, and with a dynamical black hole mass measurement. But then there have been hundreds of candidates found based on optical and infrared emission lines and confirmed by the detection of X-ray emission. The main emission lines used are the ones forming the BPT diagram, in which we have a emission line ratio here of O3 and H beta, here nitrogen and H alpha or sulfur. And depending on the location of the galaxy in this BPT diagram, we can see whether the ionization comes from an AGN or from a star formation. So applying these BPT diagrams together with the detection of broad Balmer lines of broad H alpha emission, from whose width and luminosity we can estimate the black hole mass, there have been hundreds of intermediate mass black holes with black hole masses of between 10 to the 4 and 10 to the 6 found in local dwarf galaxies. What happens is that these techniques are of course limited to very nearby sources and also to very bright sources with high Eddington ratios so that we can detect properly the emission lines and these broad Balmer components. To circumvent these limits, what we can do is to go from single fiber spectroscopy, such as the one used so far in SDSS, in which we have a single aperture here at the center of the galaxy. The problem with this is that if you have a strong star formation or a strong host galaxy light diluting the AGN signatures, you will miss the detection of an AGN in such galaxies. Also, if the AGN is of nuclear, for instance, due to a merger, or it's switched off, is no longer active, then the presence of an AGN in such galaxies will be also missed by single fiber centered apertures. So instead of that, what we can do is to go for integral field spectroscopy, in which rather than having a single fiber at the center, we have more than 100 fibers covering the whole galaxy. And we did that using the MANGA survey. We first identified all the dwarf galaxies in the survey, and then applied the BPT diagram to find spaxels, so pixels that are ionized by the AGN. And we can see here an example in which we see more than 100 spaxels ionized by the AGN. You see they are all of them located at the center. So this is a source that is not missed by SDSS single fiber observations because the AGN is at the center. However, we have other sources, such as this one here, in which the AGN emission is located here in the outskirts of the galaxy. And actually, the location of the SDSS is telling us that the source would be classified as a composite rather than an AGN. Okay, so this is a case in which the AGN might be switched off, is no longer active, and what we are seeing are the light echoes of the last burst of ionization from the AGN. And then you can have all the other cases such as this one, in which there's a lot of star formation here at the center, and we see the AGN emission located here. This can be either a case of an off-nuclear AGN, or a case in which the AGN emission here is hampered by the strong star formation light. As a result of this study, we found 23 new AGN in dwarf galaxies that have been missed by previous searches with the SDSS. If we check the volumetric luminosity of this AGN, we see that they are way fainter than any previous surveys, not only by SDSS here in purple, but also by radio or X-rays. Okay, so this population of AGN in dwarf galaxies found using integral field spectroscopy is very faint, but also hidden because we missed them in previous surveys. Okay, so using integral field spectroscopy, we can find a population of hidden and faint AGN in dwarf galaxies. And what is more interesting, this is another source of the sample, is that in this case, again, the AGN are here in the outskirts. We see that if we plot the spectrum of these red spaxels here, so of the spaxels ionized by the AGN, we see broad H-alpha emission. And from this broad H-alpha emission, we are able to derive a black hole mass of 10 to the 5 solar masses. So this is the first case of a type 1 AGN found hidden in a dwarf galaxy thanks to integral field spectroscopy. Okay, this was what we can do in the optical in order to detect AGN or low mass AGN in dwarf galaxies at low volumetric luminosities. Another thing that we can do in order not to miss these faint sources and to go to high redshifts is to look for mid-infrared variability or optical variability. This has yielded a few tens of candidates as well, but all in the low redshift regime. We can go to X-rays as well, and this yielded the detection again of a few tens of candidates up to redshift 0.6. But if you want to go to even higher redshifts, and if you want to have complete samples so that we can derive the black hole occupation fraction and therefore infer how ship black holes formed in the early universe, we need to go to deeper surveys, to wider surveys, such as the Chandra Cosmos Legacy Survey, in which we have more than 2 square degrees of the sky covered by all major facilities on Earth and also in space. We have more than 50,000 dwarf galaxies. And of these 50,000 dwarf galaxies, we found that 40 have an X-ray detection. And you see that even after removing the contribution from hot gas and X-ray binaries to this X-ray emission, we find X-ray luminosities which are very high, above 10 to the 40 x per second and up to 10 to the 44 x per second. So these are clearly AGN in dwarf galaxies out to redshift 2.4. Thanks to this X-ray survey, we're able to detect very high redshift AGN in dwarf galaxies. Another nice thing of this study of cosmos is that we can derive the AGN fraction of AGN in dwarf galaxies in two stellar mass bins, from 9 to 9.5 in logarithmic scale and from 7 to 9. And what we find is that the AGN fraction decreases with stellar mass, which is in agreement with simulation of dwarf galaxies hosting sealed black holes that form via direct collapse, in which we see that the black hole occupation fraction decreases with the stellar mass, suggesting that sealed black holes predominantly formed via direct collapse. This was in the X-rays, but of course we can also go for radio searches of AGN in dwarf galaxies. We know from individual studies that AGN dwarf galaxies have radio jets. This is the case, the famous case I showed you before, NGC 4395. We see extended radio emission here. Also NGC 404, another one, another nice case of a jet. But these are only individual cases. If you want to find more sources, if you want to have more statistics, we need to apply for either large programs or go to surveys. Range et al. What they did is to observe with the VLA more than 100 nearby dwarf galaxies in the X-band. As a result, they found, after removing contribution from star formation, 13 radio AGN dwarf galaxies. And I'm showing here one of them. You see that the VLA emission is very compact at 9 gigahertz. And I'm showing this case because in later works by Molina et al., they found that applying shock models and the BPT diagram, they found that the accretion flow is radiatively inefficient, and that the emission and that the surrounding gas can be photoionized by shocks. What does this mean? That there's possible evidence for radio feedback in this dwarf galaxy. Okay, so AGN radio feedback could also be significant in dwarf galaxies. We know that this is the case for massive galaxies. In massive galaxies, we know that radio jets can hamper or trigger star formation. However, to further understand and investigate whether this is the case in dwarf galaxies, we need larger samples. We need statistical studies. So what we did is to go back to the Cosmos survey, but now we went for the VLA coverage of the Cosmos survey at 3 gigahertz. You see that we have very good sensitivity, 2.3 microjansons per beam. And again, after removing the contribution from star formation, we found here 35 AGN dwarf galaxies with radio emission. We can see them distributed here in redshift, and we see that compared to previous optical and X-ray surveys in which we reached redshift of 0.3 in the case of the optical or 2.4 in the case of X-rays, now we reach redshift of 3.4. Note that this is a redshift record holder for an AGN dwarf galaxy, but this is a photometric redshift. The most beautiful result of this work is that for these 35 radio AGN dwarf galaxies, we find jet powers and jet efficiencies, which are very high as in massive galaxies. And actually, similar results were recently found by Davis et al. Using the LOFAR survey. They don't have such a good sensitivity as with Cosmos, yet they find 78 radio AGN dwarf galaxies with a jet power that is also very high, consistent of that of massive galaxies, in which we know that AGN feedback is present. So we are finding that AGN feedback could also have a very strong impact in dwarf galaxies, triggering or hampering star formation, and thus the amount of material available for the black hole to grow. This is another example of AGN feedback. This is the Arecibo survey. Here, the authors look for H1 observations of dwarf galaxies. We have here the amount of H1 mass, and this is in the x-axis the distance from the BPT. So sources here on the left are star forming, and as we move to the right, they become more and more AGN. And what we see is that as more AGN the sources become, the less amount of H1 gas is present. And these are isolated galaxies. So we know there are no effects, no environmental effects taking place. So this could be again evidence for AGN feedback destroying or consuming the cold gas. These results are in line with actually the detection of Asian outflows in dwarf galaxies, based on the detection of a blue wing of an asymmetry on the O3 line. Liu et al., also Manzano, King et al., they find outflows of more than 1,000 kilometers per second. So evidence for Asian outflows in dwarf galaxies. This is very recent and very new. This was not expected before, coming from Asian in dwarf galaxies. And the most beautiful and recent result is that of Genis 210. This dwarf galaxy was found to host a low luminosity AGN already 10 years ago, here at the center of the galaxy. We see here the contours, the radio contours from the VLA and the LBA. And this is the HST patient alpha image that we see in colors. Now, what they find, Schut and Rines, just in February this year, is a filament that you see here extended, connecting the black hole, the massive black hole, with a recent site of a star formation. And this filament here can be reproduced by a bipolar outflow model. So they find evidence for AGN triggering a star formation. So evidence for positive AGN feedback in a dwarf galaxy. Now, why is this so important? Because we have been assuming, as said before, that the seed black holes that did not grow, that did not become supermassive, can be found in today's dwarf galaxies as leftover intermediate mass black holes with a black hole mass that depends on how they formed in the early universe. They formed from POP3, then we expect here black hole masses of 100 to 10 to the 3. From direct collapse, we expect here 10 to the 5 solar masses. However, if feedback and mergers are important, if black hole growth is not hampered by supernova feedback, but is enhanced by mergers or agent feedback, then these local intermediate mass black holes being found here in dwarf galaxies should not be treated as the relics, as the leftover of the seed black holes of the early universe. So the question that arises now is, are then the intermediate mass black holes being found in dwarf galaxies the relics of the early seed black holes? To answer this question, we can either further investigate mergers and feedback in the local universe, in local dwarf galaxies, or we can go to redshifts as high as possible and try to directly detect seed black holes at birth. To try to go to redshift as high as possible, we use deep surveys, and this is again the VLA coverage of the Cosmos survey. I told you that we reached a photometric redshift of 3.4. Now, recent confirmation by Haiwan et al. Indicate that we have a source here at 1.9 with a spectroscopic redshift. Okay, so we are starting to detect high redshift AGN in dwarf galaxies, spectroscopic redshifts. And actually, to increase this sample of high redshift AGN dwarf galaxies, we are using the Viper survey, which was performed on the VLT. And we are looking for broadline AGN and then applying an SED fitting, a spectral energy distribution fitting to the photometry to derive the stellar mass. We select those galaxies which have a stellar mass below 9.5 in logarithmic scale. After applying this, we find that out of the 1,000 broadline AGN, 22 are dwarf galaxies which have broad emission lines. And from these broad emission lines, we are able to estimate the black hole mass. We have here very high redshift cases, such as this one here, spectroscopic redshift 2.7, and we see that it has broad carbon 3 and carbon 4, from which we can derive the black hole mass. So we can go for high redshift AGN dwarf galaxies using deep surveys such as these ones, or we can also wait for the next generation of observatories to directly detect the seed black holes. James Webb will be able to do that, will be able to discern population 3 seed black holes from direct collapse black holes based on the SED fitting. We will also have Athena and the Lynx X-ray Observatory being able to detect direct collapse black holes at redshift around 10, as we can see here, with flux limits which are way better than current surveys. One such case of a direct collapse black hole at redshift 7 is CR7. This is a strong Lyman alpha emitter found already a few years ago, which has an estimated black hole mass of more than 10 to the 6 solar masses and an estimated X-ray luminosity of more than 10 to the 43 X per second. So what we did for this source is, based on the black hole mass and X-ray luminosity, is to estimate the radio flux that this source should have using different fundamental planes of black hole accretion that you see here in different colors. Each color represents a different fundamental plane. And we plot also here the detection limits of the SKA final survey, of the next generation VLA, and of the SKA mid surveys. As a result, we find that supernovae can be ruled out for this CR7, for this source, and that using the SKA below 3 GHz, we will be able to distinguish between a direct collapse black hole and an H2 region for CR7. Okay. If we apply this to a broader range of objects, what we try to do is to estimate the direct collapse black hole mass required for detection with the SKA final survey. We find, and this is again, different colors represent different fundamental planes. This is at 500 megahertz. That with the SKA final survey, we will be able to detect direct collapse black holes of nearly 6 per 10 to the 5 solar masses at redshift 8. And a bit more massive direct collapse black holes of 10 to the 7 solar masses will be detectable at redshift 20, so very close to their formation. So direct collapse black holes at birth should be detectable with the SKA final surveys, and this will allow us to prove the formation of the first quasars in the universe. And of course, another way to detect intermediate black holes is from the detection of gravitational waves. Actually, there has been already one such case of 140 solar mass intermediate black hole detected very recently in 2021. The ring down of intermediate black holes binaries of up to 10 to the 3 solar masses should be detectable actually already with carbon interferometers, although we found only one case. But if we want to go to higher masses, then we have to wait for synergies between LISA and the SKA and LINX. These 3 observatories will prove a similar mass redshift range for early seed intermediate mass black holes. And you can see here the black hole masses that will be covered are a bit higher, 10 to the 4 to 10 to the 6 solar masses, more massive than these 10 to the 3 intermediate mass black holes here. So I've shown you that seed intermediate mass black holes are required to explain the formation of supermassive black holes in the early universe, and that they can be found in the local universe as relic intermediate mass black holes in different types of sources. In globular clusters, where accretion signatures should be detectable with the SKA and the next generation VLA, but also as wandering intermediate mass black holes in the Milky Way. Here, tens of intermediate mass black holes are expected with a bound cluster of stars around, and they should be detectable with the SKA if the intermediate mass black hole encounters a molecular cloud, for instance, that triggers accretion. Intermediate mass black holes in extragalactic sources can also be found in ULXs and as AGN in dwarf galaxies. These should be are detectable actually up to redshift 3 with large and deep multi-wavelength surveys, as I've shown you before. The jet emission, the black hole properties, we can study them via X-ray emission, optical observations, but also radio interferometry, such as the EVN or LOFAR. And at birth, seed black holes will be detectable with the SKA at redshifts above 7. However, note that for all the local studies of AGN in dwarf galaxies, we see that mergers and AGN feedback might be very significant, might yield significant growth of the seed intermediate mass black hole. So further studies are needed to understand whether local intermediate mass black holes are truly the relics of the early seed black holes. There are many results coming up, so please stay tuned, and thank you very much.
Okay, thank you very much, Mar. So we have now one question so far, so we are waiting for more. Thanks for the very interesting talk. Can you comment on the flux densities of the radio emission in a case of the intermediate black holes in ULIX and dwarf galaxies, and if they vary over time? I will also copy you to the chat. It will be convenient for you.
I can see the chat, I think. Yes. So in the case of ULXs, let me show here. Yeah. In the case of like this one here, for instance, the detection was not very significant. This was like a 5 or 6 sigma detection. It was very faint with the EVN. In the radio, it was very bright. In the case of HLX1, it's very bright in the radio. This is ad hoc observations. And the radio emission is transient. It behaves similarly to an X-ray binary. So we have cases of both transient radio emission or steady radio emission, such as in their source. Or, well, in this source, we couldn't perform any monitoring, so it might be transient as well, but we had only one snapshot. And then in other cases, such as this one, you see again that the radio emission is very bright. And here is the VLBI. You can see here the millijansky per beam. So these are sources that can be both very bright or very faint. There's no, I would say, agreement in the radio fluxes. And you can have variability or not. It all depends on the source, of course, but also on the observations, because I'm pretty sure that if we perform monitoring of a source like this, it can be that we also see transient radio emission.
Okay, thank you. So I can see one more question. What do you think about the role VLBI, especially SKA VLBI, can play in future intermediate black hole studies?
Okay. Is this another thing about the role? Yeah. What I showed was in general for the SKA. Of course, the problem, and you can see it here, of going, for instance, from VLA to VLBI is the resolution, right? So SKA VLBI will be very important for resolving compact radio emission, because if you have only VLA emissions such as this, you don't know for sure if these are star formation processes or a radio jet. So the same is going to happen with the SKA. If you want to resolve radio jet emission, you want to detect structures, we need to go for the VLBI. This in the case you want to resolve the radio jet. Of course, then depending on the redshift, will be also very important to use VLBI to discern from extended emission of the whole galaxy, so star formation processes of the whole galaxy, discern it from compact radio emission at the center of the dwarf galaxy, for instance, where the AGN is located. And sorry, in the previous question, I forgot to mention about radio variability in dwarf galaxies, so I replied only to ULXs. I'm not aware of variability studies of, so there have been recently many searches for radio AGN dwarf galaxies, but in these works, as far as I know, they don't report about variability. In our paper about VLA Cosmos radio observations, of course, these are just single observations, so we don't report any variability either.
Okay, thank you. And there is two more questions. So first, how much can the VLA Sky Survey help with this? I also copied you to the
chat. That's true. Mm-hmm. And there are works, this could be, I haven't checked that, but I'm pretty sure, this could be used indeed to look for radio variability in AGN dwarf galaxies. I'm not sure, maybe if Christina Nilan has done some work on that. It could be that some people are already working on this. Yes.
Okay, and one question from the YouTube. There is also in the chat. You said that the direct collapse mechanism only takes place under certain circumstances. What would those be?
Yeah, so you need UV radiation that directly forms the black hole without forming star formation. So there's a threshold, like a temperature above and below which, rather than forming the black hole, you will form star formation, and then you are like, you are not, it's not useful anymore for forming direct collapse. So there are certain conditions that you need to have to prevent star formation and forming a direct collapse black hole. And these conditions are, not easily met. It's way easier to have population 3 stars. That's why I said that the formation via direct collapse black holes will form less seed black holes in dwarf galaxies.
Okay, thank you. And in the chat, another question with reference to the many different lines shown in the plots on the fundamental plane of black holes. Do you know if there is anything being planned to improve the calibration of the relation, particularly in the intermediate black holes mass range?
From our side, no, here we just, I mean, we cannot improve these correlations using the SKA yet. Every now and then there are new works, new fundamental plane correlations. What changes is the sample used to derive these correlations, whether you include well, which type of AGN you include, whether these are sub-Eddington or super-Eddington accreting sources. So all these different correlations depend on the samples included to derive the fundamental plane correlations. So that's why we plotted all of them so that we can test all possible scenarios. From our side, deriving new correlations is not in my future plans for now, although it's true that now that we are finding so many radio AGN dwarf galaxies, maybe this is a possible project to be performed. Thank you.
Okay, thank you. So we will stay tuned. Thank you very much, Mar. So now please come back to the announcements, Benito. Thank you. So we are finishing the second series of the seminar, the EVN seminars, and stay tuned that the third series will be starting after the summer. So please remember to register and see you in Cork for the 15th European VLBI Network Symposium. Thank you very much. Bye.